In this video I'm going to take a look at an example of a static binomial model. Again, it's Rubinstein, CRR, and basically the tree structure is such that when we develop the tree type structure, all the values in the binomial Cox-Ross-Rubinstein tree are stored. So the snippet of code that's kind of relevant here is basically this one. We actually build the binomial code. I should acknowledge that I took the code partially from Volupta and also from project work developed by Qin Chang, who formerly did a dissertation with me, and he presented this snippet of code, and we investigated a little bit why this type of model is a little bit slower than a more dynamic type binomial construction. So in this binomial model we develop a 2x2. We define a vector that's 2x2. In other words, the data, when we estimate the binomial tree, we store that in each node as a data point, and that's a 2x2 type matrix. So it's not the most efficient, but it definitely gets the job done, and it's also good in terms of explaining the binomial construction. So we could just run a 1000-step tree here and just observe the results. And the values I put in here are values that I've taken from Broading the Temple. And for a 15,000 step tree, we would get 9.066. So just to see that, I took the same values for parameter inputs for risk-free rate, volatility, dividend 7%, with an asset price of 100 and a strike price. Also, so the strike price is also given here as 100, K equal to 100, stock price equal to 100, and that would produce 9.066, which is a true value, and the true value is based on a 15,000 step tree. So the true value column is based on binomial method with 15,000 time steps. Now with 1,000 time steps, we're finding the value obtained is 9.064. So we could potentially increase this to 5,000 and run again. And I'm using the online GBD C++ compiler. And I also have some code here that outputs, well, we have 10 digits that will be reported in the output. And we also get the time it takes for the estimation to be completed. So it takes 3.49 seconds to do a 5,000 step tree. We can go completely, we can put in 15,000 steps here, look at how long that takes. Again, we've got to be conscious that it's not going to be fast. So with 15,000 steps, it may be actually the case that it'll abort because the estimation is too big. Okay, so the estimation here is killed simply because we increased the step size. But if we bring it back to 5,000 steps again, we're saying for this data for this code to load up onto the server and to report back the results, it takes more or less about 3.49 seconds for the estimation to be completed using the code that we have here. So again, okay, 3.6 seconds, and we're getting a value of 9.65. Okay, so it's obviously an issue here. The number of steps is taking up too much memory. If we go above this, if we take this up to 15,000, for a call option and for an American option, we're finding that we're not able to recover this value. We get close, but of course there's difficulty getting up to the 15,000 steps. One of the issues then is that the code is static. And just to see what I mean by that, in the type of estimation performed here, we build a tree, and at each node we store a data point. So for instance, we could take a look at what that entails. I have a simplified, again it's not terribly simplified, but I have a 15-step tree here, and a space and a stock price, and I put in parameter values for the stock price, the exercise, the maturity, the interest rate, volatility. B here denotes cost of carry, and it's just R negative Q. So if we have a negative 0.01 B, that implies that Q is equal to 8 if R is equal to 7, risk-free rate equals 7. And again, it's 15 steps. And how do we run the estimates? Well, we basically take the stock price, the initial stock price has been 100, and then we take, I have an array output here, and it has the up and the down based on Cox-Ross-Rubinstein, and a risk-neutral probability, again based on Cox-Ross-Rubinstein, and we generate this Cox-Ross-Rubinstein tree. So for instance, if we take this cell here, I multiplied 100 by D, I got this value. I multiplied by D or down again, I get this value. So this row of data is basically each successive cell is multiplied by D, and it corresponds, if you want to look here, corresponds to this blue lower set of nodes here in this Cox-Ross-Rubinstein tree. Notice well, when we generate the tree here, the values closer, the lower values for the stock price tree tend to cluster together, and as we increase the stock price, it goes up, and that's a feature. The Cox-Ross-Rubinstein tree is slightly curved. Again, probably would see that better if I increase the level of volatility to 40%. If I come back down, if I come back up and just return, 40 has changed here, but also notice that we have this much greater fanning out of the values. Again, there's clustering here at the bottom, but there's a fanning out of the values here, and that's typically what we observe. So basically the data set contained here in this vector, it's a 2x2 vector, is then produced or set up here, displayed here in the graph. And okay, so that's fine. So our job here would be to estimate, maybe we can take that value back to 0.2 for a second and just look at how the fanning out alters, right? When we look at the 0.2 here, right, there's much more clustering again, right? So there's a fanning out as we increase to 0.4 the volatility and so on. So if, again, we can play around with this. I'm not going to play too much, but the main, what we observe here, if we set up an American, we want to value an American option. I have some code here that I borrowed. Just have a dedicated Cox-Ross-Rubinstein function in VBA, and basically for an American option its value would be 205. So if we change any of the values here, changing values here will produce changes here, but the value of an American call option with 100 stock price and 110 exercise and with the other parameters is 2.05, and for a European option 2.02. So that would suggest that there's some early exercise going on with the American option because it's more valuable. Also to look at how the American valuation is done here, as before, like any Cox-Ross-Rubinstein tree, the final set of nodes, right, is just basically the difference between whatever the stock price is on the highest stock price minus the exercise. And again, if I highlight this cell again, I'm coming down. So I could take this cell and just pull it down, and you can see the values are the maximum of S minus X. So that's what the call option represents, the intrinsic value obtained here in the final set of nodes. But then the preceding cell, for an American option, we've got to judge the maximum of S minus X, again S minus X, and then we have P. P is the risk neutral probability, Cox-Ross risk neutral probability. W1D, value of the option of the stock price goes up, and plus 1 minus P by W20, the value stock price, the value of the option if the stock price goes down, and then we discount it at the risk-free rate, which is this df that I have here. And again, so basically this cell is iterated. I can pull that cell down, and again I just replicate everything that's there. And again, so that's a manual construction, and we can note here that the value of the, if I do that, the value of the American option is equal to 2.05. I do likewise using European type construction here, and the value here. So the value here also 2.022, which is captured here with the European option. Again, I'm using a VBA function here. Okay, now just to see, can we replicate those results in our static model? Well, I'll look for our static construction again, and here we can just change the values. So we might just load up okay, so I'll pause and rearrange. I have the two sets of parameters here side by side, and I'll just enter in the values here. So this is again 100. This would have been 110. The value here for the time period is 0.5, so I changed the time period, and again I'll pause and I'll put those values. Okay, so I've taken the parameter inputs here, 100, 100, stock price, exercise 110, 110, the time period is 6 months, the risk-free rate is 7%, but B, which is R negative Q, it's the cost of carry, is -1. The only Q consistent with negative 0.01 B, cost of carry, would be where the volatility was 8, and where the dividend was 8. The volatility is 20%. We have that. When we run this, again, we can run here. When we run this estimate, again, it's not 5,000 actually, it's just 15 steps. So we can look at the value, but it's not 5,000 we're trying to demonstrate, it's just, okay, so I'll just stop and I'll put in 15. And I run again, and this will be fast. Relatively speaking, is okay, 2.0508, and that's the result I have here. And then if I change, just make one change, instead of it being American, if it's European, E. Okay, and run again. We find that the value should be the same as the value that we have here. The 2 points, okay, so 2.02201. So this model looks as if it's working, it's fairly decent. It's also consistent with the values. This value is the same as the value from the manual tree. And if I come across then to the European construction, the 2.02, I mean, we can copy that value, home, copy, and just do a paste special value, and we also get a value 2.02201, 2.02201. Okay, so the European option is, we're producing the same value here for the European option.